Hello students, if you remember in last part we have derived the theoretical proof of E equal to minus d phi by dt, that is nothing but what? A translational motion of a conductor when it was kept in a magnetic field. That part we have finished. Now the same part, the second part is remaining. That part is nothing but what? Motional EMF in rotating bar. Here that initially we have seen the coil is kept here and this bar is moving toward the coil and moving away. This is the coil, this is a magnet, it is sliding toward or away. It is a linear motion, straight line motion, that is said to be translational motion of magnet. Now what we have to see, the magnetic field we have kept and we have, instead of translational motion we have rotational motion. Suppose this is a coil, conducting coil, and now it is kept in magnetic field and it is rotating like this. In magnetic field it is rotating, and as the coil is rotating in the magnetic field, definitely there is changing magnetic flux linked with the coil, and due to that there must be production of induced EMF in the same coil. So that we want to consider here. So as according to the book, just I will draw here one of the small coil. Just suppose this is a small coil and here this is a small area of the coil. It is said to be dr. Dr is a small length of the coil, not the area, length of the coil, which is moving with the velocity v. In a magnetic field it is moving with the velocity v in angular motion, and total length of this bar is suppose L. So total length of the bar is L, and the length of the element dr get from this pivoted end, it is suppose they have taken this as, I think it is taken as a R. So let us consider this is R. Apart from this plus type of circular part they have shown in your book, these are nothing but what? Magnetic field applied perpendicular to board. Now this plus sign indicate the magnetic field applied perpendicular to the board. So these are the perpendicular to the board magnetic field we have applied. So this circle represents the perpendicular magnetic field applied to the board. Now as the particle of this coil is moving with the velocity v in angular motion whose length is dr. If you remember, just initially for translational motion we have find out that magnetic field, just if you remember we have derived this equation E equal to B into L into V. This is for translational motion we have derived, if you remember that part. So this already we have derived equation 12.10 from your book. Now here for the small element dr whose length is dr, so instead of L you should take a dr. Instead of EMF induced E, here EMF induced is suppose dE. So we can write dE is a EMF induced in the coil whose length is very small, that is nothing but a dr. The coil has a length of dr, EMF induced in it is dE, magnetic field applied is B, coil is moving with a velocity v, its length is not L, it is what? dr. By this equation you can write dE equal to B into, what is the length? Length is nothing but a dr into V. B into dr into V, or you can write this as B into V into dr. This is nothing but a EMF induced in a small length of the coil dr. Now suppose I want to find out total EMF induced in this coil. This is for dE for this. And if we add this area a little bit here from this end to this end, that will give the total EMF induced. That can be found out by integrating this. If we integrate this dE, integrate this term from 0, dr changes from 0 to maximum L. So 0 to L, we will get a total EMF induced in the coil. So we can write here, I will write this below. So we can write here integration of dE is E equal to B and V, that are nothing but just we have kept. Now what is the V equal to? If you remember in rotational dynamics we have learned V equal to R omega. So we can write integration 0 to L B into V equal to R omega. So R into omega into dr. R into omega into dr. In this case this B and this omega are constant. So take them outside of the integration. We can write this as B into omega omega integration varies from 0 to L R into dr. So that will give nothing but what? EMF induced in the circuit. Now in the coil, circuit in the sense in the coil. Now we want to find out integration of R dr. It is nothing but what? R square divided by 2. So we can write this as B into omega R square divided by 2. The limit varies from 0 to L as it is. That is nothing but the EMF induced. Now put upper limit instead of R, then lower limit instead of R, subtract them. So it becomes L square by 2 minus 0 square by 2 means 0. So finally what we get here, B omega into L square divided by 2. This much EMF is induced in a coil rotating with a velocity, angular velocity omega. If we see here, it is B omega L square by 2. I will write this equation little bit to this side. This side I will write same equation, E equal to 1 by 2 B omega into L square. B omega into L square, that is the EMF induced here. E equal to 1 by 2 B omega L square. If we compare this equation of EMF with this equation for translational motion, this is for rotational motion. B is common in both. V, here it is V, linear velocity because it is a linear motion in this case, so linear velocity. Here it is omega, angular motion, it is moving circularly with angular velocity, so omega. B, omega are there. Here it is single L, here it is L square divided by 2. That is the difference between the translational motion and the rotational motion, rotating magnetic bar and translational magnetic bar. In this fashion, this part we have covered. Now the next 2 points, just skip this here from your examination point of view. Directly we go to page number 276, that is induction and energy transfer. How the induction and energy transfer get occurred, that we have to learn. So I will drop this. Now we go to the next topic of our syllabus that we have to see now. How the induction get occur and how the energy get transferred, that we have to see. So the heading is induction and energy transfer. So it is induction and energy transfer. What is induction and energy transfer, that we have to see now. So to understand this part, so just we have to draw one diagram. I will draw the diagram first. So if you remember, such type of diagram already we have drawn earlier also. So this is the dotted lines. I am going to draw this dotted part, explain the, or just it will give the magnetic field applied within this dotted part. It is a perpendicular to board, and within this part here some smaller part, the rectangular part they have drawn. So this is the coil. This is the coil which is moving inside this with some velocity. So here this is a coil, just I will remain it like this, and they have given the name to this coil as a ABCD. So this is A, this is B, this is C, and this is D. ABCD is a coil kept in this dotted square. Dotted square is nothing but what? Magnetic field applied. Magnetic field is applied within this dotted square. That's why in your book just they have given the plus sign and circle. So plus sign and circle, that already I have told you, these are nothing but what? Magnetic field applied perpendicular to the board. So these are the plus sign they have shown to represent the magnetic field. I will not write the inner part, just in your diagram they have mentioned here also. So here also we should represent the magnetic field. So these are the magnetic field applied within dotted portion, and ABCD is our coil that was kept in the magnetic field. Now here we have to pull this BC part at outside with some velocity. Suppose V, I am moving this outside with some velocity V. Apart from this, when this coil is kept in magnetic field perpendicular to the plane of the board, it is seen that 4 forces act on it. What are the 4 forces? One force act in upward direction, another in downward direction, one to left hand side and another one to right hand side. So upward force is F2. This they have taken as F2. It is F2. This is nothing but what? F3, and this is nothing but what? F1. That is nothing but what? F1, and here we will consider this as a force F. So these four forces act on the coil. So what we are going to do here, just I am standing here, I have hold this part, we can move it inside and just take it outside, inside and outside. That part is nothing but what? The coil experience changing magnetic flux, so EMF is induced in the same coil. So before going in detail further, just I will try to write down here what is the dimension of this. So the length of this thing is nothing but about this loop has a length here, this length, or we can say width, that they have taken as a L is a width, and the part of the coil which are in a magnetic field up to this dotted line, that part which is in the magnetic field, that was represented by X. That was represented by X. If you remember, same type of diagram already we have learned. So when we move this BC to outside, X decreases, L remains constant, X decreases. When we pull the coil inside the magnetic field, X increases. In short, X is varying here. Now what we have to do? We have to mathematical equation we have to derive. For that, just we will write down some equations. The basic equations we will write down. The rate of doing work on a loop is, rate of doing work on a loop means I am moving this inside and outside, means I am doing some work on this loop. That work, rate of doing work, how the work is done with time, rate of work doing on the coil, that we have to find out, and that I will write little bit to this side. Just I will switch the camera to little bit aside, we will move the camera and just try to find out the equation, basic equations we are going to find out. So just I will write down the remaining equation to this side. So basic derivation starts now. So here rate of doing work on the loop, that was represented by P. So we can write here, just I hope you are visible. Yes, P equal to, this P is nothing but what? Rate of doing work on a coil is equal to what? Work done on a coil divided by time taken to do the work done. Work done on a coil, or work on a coil divided by time. As we know, what is work? Work is nothing but a force into displacement. So into force into displacement divided by time. If you see displacement divided by time, that is nothing but velocity. So you can write here, it is force is F and displacement divided by time is velocity. So P equal to force into velocity, suppose equation 1. Force into velocity, suppose equation 1. Now we know another part of this, nothing but what? Magnetic flux linked with this coil which is moving in magnetic field. That magnetic flux can be written as phi suffix B. Magnetic flux linked with the coil moving in magnetic field is equal to what? Magnetic induction, that is B into area of the coil A. That also we have seen in last period. Magnetic induction into area. Now area is what? Length into width. So here we can write this as B into length is L, width is X. B into L into X, that will give the magnetic flux. Now as this magnetic flux is linking with the coil during its movement, during its motion, then there must be production of EMF in this. According to Faraday's law, EMF induced in the coil, small e equal to what? Minus d phi by dt. So to avoid the minus sign, what they have taken? They have taken this is in mod. Mod of E equal to d phi by dt. In magnitude you can write. Now put the value of phi b this here. So we get here, it is d dt of B into L into X. B into L into X. B and L are constant, so take them outside. So I will write E equal to B into L are constant into dx by dt. Dx by dt means rate of change of displacement with time. That will give the velocity. So we can write B into L into V. That is the magnitude of EMF. This equation also already we have derived earlier. This equation also we have derived earlier. Now here I will write this as equation 2. I will write this as equation 2. Now we know, according to Ohm's law, we know, if you remember, Ohm's law might be you have learned in 10th standard and we have learned in 11th also. V equal to IR, where V is a voltage, I is a current, R is a resistance. In our case, what is a voltage means EMF. In our case, it is what? Instead of V, we are using induced EMF. Instead of current I, we have induced current I, and suppose the resistance of electrical circuit is R. This is Ohm's law. This we have applied to our case. If you have the book, figure 12.9b is there in the book. You can see that from that figure, E is the induced EMF, I is the induced current, R is the resistance of that electrical circuit. We can write this equation. Okay, once you can write this equation, from this find out the value of I equal to what? E divided by R. So from this we can write I induced EMF equal to, induced current equal to induced EMF divided by resistance. So we put the value of E. What is the value of E? B into L into V. That value we can put it here. So put this value of E. So we get here B into L into V divided by R. That is nothing but a induced current given by equation 3. Equation 3 gives the induced current. Now let's go to the forces. If you see, just see the diagram. There are four forces: upward force, downward force, left hand side F1, here it is F. As their forces are exactly same, so upward force F2 is cancelled with F3. So this force F2 and F3, they are exactly same in opposite direction, they get cancelled out. Now we are moving this coil outside with some force, so that force F must be exactly equal to F1, but their direction is opposite. F1 goes to left side, F goes to right side. So we can write here simple equation for these forces. We can write F equal to minus F1. F equal to minus F1, because both are the vector quantities, they are moving in opposite direction. So we can write F equal to minus F1. How to find out this force? There is one equation. That equation given in your book also. I will write that equation little bit. I will write it here. Just you can visualize this. There is one equation. F equal to. There is one equation. F equal to IL cross B. I into L cross B. All these are the vector form. This equation gives the force to us. F equal to I into L cross B. This equation gives us a force. From this equation we are going to find out a force. Now how to find out a force? Just use this equation. Cross product is there, there must be sine theta. So you can write here magnitude of F equal to magnitude of F1 is equal to this IL cross B, means in magnitude what? I into LB sine of theta. Theta is angle between L and B. LB sine of theta, and L and B are exactly perpendicular to each other. So this sine theta means sine of 90. Sine of 90 is 1. So finally we can write this as equal to ILB. That is F equal to F1 equal to I into L into B. So that is the equation for forces F1 and F, which are exactly opposite to each other. Now from this, just I is there. We know the value of I is given by 3. This equation 3 gives the value of I. Just we are going to put the value of I in this equation and rewrite the equation. So just this equation I am going to write at the top again in terms of putting the value of I. So what we can write? We can write here F equal to F1 equal to F equal to F1 equal to, what is the value of I then? BLV divided by R. So BLV divided by R, that is the value of I, into LB as it is. So just I will make the camera a little bit above. So what we have done? We have written BLV divided by R into LB as it is. If we solve it, what we get? B square L square into V divided by R. That is nothing but a force required to move the coil in a magnetic field. F equal to F1 equal to B square L square V divided by R. Suppose this is equation 4. This is equation 4 that will give the actually how much force is required. Now if we see from equation 1 that just I have written here, equation 1, P equal to F into V, and we have find out F now. So put this value in equation 1, what we get, amount of work done required to move the coil in a magnetic field, P equal to F is what, B square L square into V divided by R, this equation, into this as a V. So V into V is a V square. So we can write B square L square V square divided by R. That is nothing but a P. Amount of work done applied on a loop, that is equation 5 suppose. Amount of, that is a rate of doing work on a loop. Rate of doing work on a loop means the coil. Loop in the sense it is coil in the circular or rectangular loop type, so it is loop. So this much rate, P is nothing but rate of doing work on the loop, and that we have find out, that is in the latest equation is 5. Just we have put the value of F in equation 1, we get equation 5. Okay, further just I want to find out, just in this equation just electrical circuit they have shown 12.9b. So in that figure, just if we want to find out, as current is moving, current is induced and it is moving, EMF is induced, and a circuit which has a resistance, electrical resistance R. So we know that whenever there is a production of EMF and current is moving, there must be heat produced. How much heat is produced? Rate of production of heat. So heat produced in the coil, that we have to find out. Suppose we represent that also by P, that can be find out, P equal to I square into R. P equal to I square into R. That is a formula to find out the amount of heat produced in any conductor, that can be find out by this formula. We know the value of I, that was given here somewhere by equation 3. If you see equation 3, BLV divided by R. So just put that value here, I, so it is square, so we can write B into L into V divided by R, its whole square into R. That is nothing but we have put the value of I from equation 3. Now if we solve it, what we get, B square L square V square, one R get cancelled with this R, so R is remaining here. B square L square V square divided by R, that is nothing but what, heat produced was given by this equation. Suppose this is equation 6, which will give the amount of heat produced. Now if you compare equation 6 with equation 5, if you compare equation 6 and equation 5, what do you see? Just the right hand side, B square L square V square by R, B square L square V square by R. Right hand side is same. What does it means? Left hand side must be same. What is left hand side? This P stand for work done, rate of doing work on a loop. P means rate of doing work on a loop must be equal to heat produced in an electrical circuit. So what we conclude from equation 5 and 6, as right hand side of the equations are same, left hand side must be same, and from left hand side we can say the rate of doing work on a loop, that is P, represented by blue line, rate of doing work on a loop is must be equal to heat produced in electrical circuit, and this is the conclusion we have drawn from this derivation. So this is nothing but a part that we have learned. Now next part is nothing but an AD current that we have to learn. Just I will drop. If you have any difficulty up to this, you can just ask me anytime on my WhatsApp number, or you can contact me. We will discuss further. But I don't think that there is any difficulty. Little bit mathematics we have used. Mathematical part in this, just we have put the values and we have solved these things. Now let's go to the next topic of your syllabus. That next topic is nothing but what? AD currents. What exactly the AD current and how the AD current comes here, that we have to see. So just see AD current. So I will write it here, AD current, E-double-D-Y. It is said to be AD current. What are these AD currents are, that we have to see. So here these AD currents are nothing but what? When the metal plate, instead of conducting wire, we have kept metal plate in the changing magnetic field. changing magnetic field is there, and we have put a metal plate in that. In that case, automatically some circular loop like currents, whirlpool like current get produced in the metal plate, and that current produced is said to be eddy current. Suppose we have water. Suppose this is water. Okay, this is water. When we drop a stone here, what will occur? It will produce a circular waves like this. They are moving toward the edges. These circular waves are said to be eddies. These circular waves are said to be eddies, or it is said to be whirlpools. Whirlpools or eddies of water surface. Same thing. Now we have, instead of dropping water on a stone on a water surface, suppose we have the metal plate. This is a big metal plate we have. When this big metal plate we have kept in changing magnetic field. Changing magnetic field, we have kept this big conducting plate. It is seen that it will experience changing magnetic field. Some EMF is induced in the plate and some current get produced in that plate, but that current is moving in circular path, loop like structure like this, and this loop like current produced in a plate when plate is kept in a changing magnetic field. This resultant current is said to be AD current. This resultant current is said to be AD current. Now, point to remember, it is not good to produce this AD current in a conductor, because it will dissipate the energy and it will increase the heat. As this current is moving, just before we have derived the equation for production of heat, I square R. So this AD current get produced, it is moving in the plate, metal conductor, it will produce a heat inside the metal conductor. And whenever there is production of heat, there is dissipation of electrical energy as well as magnetic energy. To avoid this, what the scientist has tried, just instead of doing this, suppose this metal plate, just I will write down this metal plate like this. Just you know how the eddy currents are produced. This metal plate we have. Now I want to reduce this current in the metal plate. So what I will do, I will make some grooves in the plate. How the grooves are made, just look at this. So I have made one this groove like this. We have to make one such type of grooves. Just curve this plate like this part get removed, again remove this part here, so this part also get removed, again remove some part here somewhere, so this part of the plate get removed here also, so this part get removed. Now what will occur? Current get produced, but that current is not circular current. See, to suppose electron is here, he has to make a circular current like this, he has to make some circular current like this. Suppose I will draw the dotted line, so he has to make some circular current like this. That electron can't do this circular current. Why so? Because here this portion is removed, so electron can't jump from this part to this part, it can't jump. Again this to this it can't jump, this to this it can't jump, because this much material we have removed, we have made a groove to the plate. So to travel electron, it can't travel like this, it has to go here and comes here, again goes here and comes here, again goes here and comes here. It will take a lot of time, and that will reduce the heat produced in a conductor produced due to AD current. Heat produced in a metal conductor can be reduced by making such a groove to the plate. And same thing they just explain in the diagram. Just if you have the book, figure 12.10a, metal plate they have taken, they have kept the metal plate in a changing magnetic field, or we have moved the plate up and down. So same thing. Then B diagram gives the how the eddy currents are produced. C diagram shows us such type of diagram plate they have shown, which will reduce the eddy current produced inside the material. So these eddy currents can be reduced by making a grooves to the metal plate. So that we have seen up till now. Now let's go further. What we have to see? Self-inductance we have to see. Self-inductance. So just I will write here self-inductance. Self-inductance is one of the parameter that was represented by capital L. It is said to be self-inductance. Might be all of you have heard about self-respect. Self-respect. You must keep respect about yourself own. That is said to be self-respect. Similarly, self-induction is one of the phenomenon here, where suppose we have some coil. So just I will draw it here. Suppose we have some coil. Just I will write again. So we have to take one coil. To that coil we have applied suppose this is a current, sorry, this is the loop. I am going to draw the coil. So suppose this is a coil, this is the coil, we have taken a coil. another end is here, one end of the coil is here, other end is at the bottom. To this coil, suppose some rheostat resistance is applied like this. This is changing resistance, variable resistance is applied. To this the battery is applied. So this is positive, positive and again negative part is applied, and here somewhere there is a key. This is a key, this is a battery eliminator, it is a rheostat, and it is connected to another end. So such type of coil is connected in electrical circuit. So K for key, E for battery, R is for changing resistance, it is set to rheostat, and this is a coil. If this coil is connected like this, when key is open, no current pass to the coil, there is no production of EMF and induced current in the coil. Okay, but as soon as when we close this key, like this, when we close means switch on the key, what will occur? Some current try to pass through the coil in this direction. Current passes from positive to negative, so it will pass like this circular part and finally comes here and goes here. So current passes when we switch on the key, or close the key, we can say. So during this motion what will occur? So initially switch is closed or it is off, no current is zero. How much current is this? I will let it here. I will let it here. I equal to 0 when switch is in off condition. When we switch on the condition, switch close, I get increase from 0 to I get increase from 0 to I. Current get increase. Changing current will produce what? Changing magnetic field. Ohm's law. If you remember, through the conductor, current is moving, it will produce a magnetic field around it. This is Ohm's law. Same way, this coil is a conductor. Current is changing from 0 to maximum value I. Changing current produces a changing magnetic field. And changing magnetic field, we have kept the coil. The coil is kept in changing magnetic field, and according to Faraday's law, whenever there is a changing magnetic field or changing magnetic flux and coil is kept, there are merged with production of EMF in the same coil. EMF is produced and some current get induced in the same coil. According to Lenz, its direction is exactly opposite to this current. So this current is moving like this. So due to changing magnetic flux, according to Ohm's law, exactly opposite current get induced, that is I, small I, induced current, exactly opposite to this, and EMF is induced in the same coil whose polarities are, this EMF comes in the polarities positive here, negative here, exactly opposite to the battery eliminator. That is according to Lenz's law. And this thing, as we are changing a current to this coil, we are changing a current to this coil by switch it on the key, current to the same coil changes, it will induce a changing magnetic flux, changing magnetic field, it will produce or induces current and EMF in the same coil exactly in opposite direction. This phenomenon is said to be self-induction. Self-induction means what? Due to changing magnetic field in the same coil, EMF is induced and current is induced due to changing magnetic field. That phenomenon is said to be self-induction. So if you have the book, in the book figure 12.11 is there. Below that they have given the definition. I will read it once. The production of induced EMF in the circuit or coil. Production of induced EMF in a coil itself on account of change in a current in the same coil in it is termed as phenomenon of self-induction. This is said to be phenomenon of self-induction. So I hope all of you understand how the self-induction work. So in the same coil, current changes, it will induce a changing magnetic flux, and the same coil, due to changing magnetic flux, EMF is produced and current is induced, and that phenomenon is said to be principle of self-induction. Now here we have to derive mathematical part. Amount of magnetic flux linked with the coil is directly proportional to current flowing through the coil. If more current can flow, more magnetic flux changes. So phi is directly proportional to I. If I remove proportionality sign, you can take equality sign. It is equal to equality. Some constant we should take into I as it is, and this constant of proportionality is said to be coefficient of self-induction. This constant of proportionality is said to be self-induction, or sometimes it is said to be coefficient of self-induction. So this thing we have done for a coil, single turn coil. Suppose we have the coil which has capital N number of turn. Number of turns are n in number. So we have taken a, might be just well known about a thread. We have taken thread, just we want to wound the thread on it. We start from this point, just do this is one winding, one turn, again one, two turns, three turns, four. How many times we are winding that thread on this, that is said to be number of turn. Now instead of thread, we have taken a copper wire or metal wire and just we are wounding it like this. Start here, goes back, come again, one turn, two turn, three turn, four turn. In general, it is n. Capital N is a number of turns. Suppose, then we can write the same equation. This equation phi directly proportional to I can be written as this is for single coil, 1 into 5 we can say. Single turn 1 into 5. How many turns now? N. So it is N into 5 suffix B. Magnetic flux is changing, kept in magnetic field, directly proportional to current. Remove the proportionality sign. You can write N into 5B equal to L into I is equal to L into I. From this you can find the value of L. So L equal to what? N into 5B. This is 5B divided by I. That will give the coefficient of self-induction. That will give the coefficient of self-induction. By that equation, you can find the coefficient of self-induction. Now, according to Faraday's law, we know whenever EMF is induced, how much amount of EMF get induced? E equal to minus d phi by dt. Just put the value of phi as this one. Put the value of phi as this one, and just we want to solve it further. So what we get, just you can put this equation or you can put this equation. So we get E equal to d dt of with a minus sign. What is the value of phi? Value of phi from this is nothing but a L into I. L into I. L is constant, take it outside, it is minus L di by dt. E equal to minus L into di by dt. That equation we get E equal to minus L into di by dt. From this find the value of L. What we get? L equal to E divided by di by dt with a minus sign. E is measured, it is EMF is measured in volt, current measured, di is measured in ampere, time is in second, and this is a unit of this self-induction, volt per ampere into second, that is said to be equal to Henry. The unit to measure this is nothing but a Henry. This Henry is a unit. 1 Henry equal to 1 volt per 1 ampere per 1 second. That is nothing but just I will show you like this. So this is nothing but what? E divided by di by dt. E is measured in volt, di is measured in ampere, dt in second. So this unit is said to be Henry, and self-induction is measured in terms of Henry. I think it's sufficient to do today. So just watch the video first, then read the same topic from your book, then again watch the video. Definitely you get whole topic from a book. Still, if you have any problem, any kind of problem, you are free to ask me any time, anywhere you can ask me. If you have the problem with a physical meeting, you can just message me on WhatsApp, or I will try to solve your query. Now next topic we will see the definition of self-induction in different aspects. The definition they have given, 3 type of definition they have given, that we have to see in next period. Then inductance of a solenoid we have to see, then the energy stored in magnetic field, and then mutual inductance we will see. Why the mutual inductance and self-inductance are very important? Because we have to see the device that is said to be transformer. In that transformer we have to use the self-induction and mutual induction phenomenon to learn the device transformer, how it works. So just watch the video, and if you have difficulty you can contact. Thank you.